This type of thermodynamics question here relies upon two facts. One being that enthalpy, entropy, and free energy are going to be state functions, and the other is Hess's law of heat formation. Let's pick that apart and start off with state functions. So a state function means that it doesn't care about the path at which we've taken to get to somewhere. It just cares on where we're at. So the analogy of that is, for instance, a mountain where we have a village on it. It doesn't matter whether we trek from the top of the mountain to the village or from the bottom of the mountain to the village. We still end up in the village. The village is still located in the same place. Now that kind of sounds intuitive, but that's what a state function means and what it means for the enthalpy of a reaction, an entropy of a reaction, and the Gibbs free energy of a reaction. The other thing that we need to actually understand is Hess's law of heat formation. Now let's do another thought experiment with now another village on the mountain here. Say we want to work out the difference in height between these two villages, but we don't have that information available. What we do know is how high it is from the peak to this village and how high it is from this village to the peak as well. So it's quite easy to see that really the difference in height here between these two villages is really this height here, height 2 minus height 1. So that's kind of like what Hess's law of heat formation will do. Let's actually dive into this example and see if we can use the same sort of analogy in the chemical sense. This question here says we've got mercury sulfide in the solid state reacting with oxygen gas to produce mercury liquid and gaseous sulfur dioxide. You can see there's one mercury on both sides, one sulfur on both sides, and one oxygen on both sides, so we have a balanced chemical reaction. Now, we're given some data here, some heats of formation, and we see that we have heats of formation of mercury sulfide and sulfur dioxide, but we don't have a heat of formation of oxygen gas or mercury liquid. And the reason for that is that they are pure elements in their most thermodynamically stable state. So oxygen is going to have a heat of formation of 0, and mercury is also going to have a heat of formation of 0 as well. So what does the heat of formation of mercury sulfide mean? Well, if we think about the energy scale here, 0 being where the elements are at, and let's look where mercury sulfide would be. Mercury sulfide would be down here at minus 58.2 kilojoules per mole. How we're forming mercury sulfide is we're going to add together mercury liquid and solid sulfur. The other thing that's going to be here is oxygen. So oxygen is going to have 0 energy because the heat of formation of that is going to be 0 by definition. So that's going to react to give us mercury liquid, and again it's another element, so mercury liquid is going to have a 0 heat of formation associated with it. Now we're going to have a heat of formation associated with sulfur dioxide gas, and we know that heat of formation is going to be minus 296.8 kilojoules per mole. How we got to sulfur dioxide? By combining elements. Well, we're going to have solid sulfur plus oxygen gas to give us that sulfur dioxide. So all of our elements are sitting here on 0. All of our compounds now are sitting out here. So if we think about this, if we sum these energies together and sum these energies together, we can get the change in energy of this reaction in a very similar fashion to our height difference of our two villages on our mountain. If we sum these two energies together, we can see the sum of each one of these delta H formation of our products minus the sum of the heat of formation of all of our reactants is going to equal our delta H reaction. And what we've done really is we've kind of derived the formula which we use to actually work out the heat of a reaction based upon the heats of formation of a compound. Now, another way to think about this using Hess's law of heat formation is to go, well, we're going to form mercury sulfide. How are we going to do that? By adding pure solid sulfur with pure liquid mercury to form our mercury sulfide solid. And the delta HF of that reaction was minus 58.2 kilojoules per mole. What was the other thing that we had? Well, we had sulfur dioxide. How do we make it? Sulfur solid plus oxygen gas gives us sulfur dioxide gas, and our delta H of formation of that was minus 296.8 kilojoules per mole. This kind of resembles the components of our total reaction that we're trying to get to, because our total reaction that we're trying to get to is mercury sulfide plus oxygen gas goes to mercury plus SO2. So we can see we've got SO2 kind of on the right side, we've got oxygen kind of on the right side, but this mercury sulfides are on the wrong side and our mercury is on the wrong side. So how about we flip this reaction around here so that we have mercury sulfide going to sulfur plus mercury. If we do that, obviously it's no longer going to release energy, it's going to take energy to do that. So we need to change the sign of that reaction. If we were to add this reaction and this reaction here, I'll just label it 1 and 2. If we were to add 1 and 2 together, we'd get the reaction that we're trying to get, because our sulfurs would cancel out. Then we've got mercury sulfide, yes, oxygen, yes, going to mercury, yes, and sulfur dioxide. Excellent. We could add these two numbers together to give us our delta H of our reaction. It's minus 238.6 kilojoules per mole. So this is the Hess's law way of doing it, and we get exactly the same value as we do with this method here. So you can see we can get the heat of reaction just by thinking about the heats of formation of compounds. So now let's move on to the entropy of this reaction. And entropy is also another state function, so it doesn't care about which pathway we've taken to a particular substance. It only cares about the difference in those states. It only cares about where we are in the scheme of things. It doesn't care about our pathway which we've used to get there. We can see here that now the entropy of oxygen is not 0, because the third law of thermodynamics says that the entropy of something has to be 0 at 0 degrees Celsius. So we can see at 25 degrees there's going to be some motion of molecules, so there's going to be some entropy involved in the material. Likewise with liquid mercury, it's going to have some disorder associated with it. So how would we work this out? So the delta S of the reaction is going to be, S0 reaction is going to be the sum of the number of each one of our products times the S0 of our products minus the sum of the number of all of our reactants times the S0 of our reactants. So doing that, we've got 1 of each one of our products here, so it's 1 times the entropy of our mercury there, which is 76.02, plus 1 times the entropy of our sulfur dioxide, which is 248.1. We're going to take that away from the sum of our two reactants. So first of all, we've got mercury sulfide, which is 82.4, and we're going to add that to our oxygen, which is going to be 205.1. And totally, that's going to work out to be a value of 36.62 joules per mole per Kelvin. So that's our delta S of our reaction, our entropy of our reaction. And before, we worked out that our enthalpy of our reaction was minus 238.6 kilojoules per mole. So now we can work out the Gibbs free energy of this reaction by knowing that the Gibbs free energy is our enthalpy of our reaction minus T times the delta S of our reaction. So that means we can substitute in what we know. Okay, you can see I've translated the number here from kilojoules into joules because our entropy of our reaction is going to be in joules. So we're at 25 degrees. We're at 25 degrees, which is 298 Kelvin, and times that by our entropy here is 36.62 joules per mole per Kelvin. And our temperature is here in Kelvin, so they're going to cancel each other out. So we get a total value of 249.5 kilojoules per mole.